Hello, good evening, everyone. So, welcome back to the problem solving session for the course of Division in Multi Component Solids. And the course ID is NOC24MM17. The course instructor or course guide is Dr. Kaustubh Kulkarni. And this is a PhD scholar, Sachin Kumar, who is taking the live problem solving session, in which we will be solving the some of the problems which are related to the current week, as well as we will be solving some of the previous concepts oriented questions. Also, we will be recapping, making a revision for the concept that have been covered in the current, and that is in past week. So this will be helpful for solving the uh, most of the different questions, as well as uh, solving for the your final exams. And one more thing, so you can also ask doubts, or you can ask some questions regarding with this, regarding any of the topic that has been covered in the previous weeks also. If I am able to answer, I will answer here itself. Otherwise, I will communicate through a mail by making a solution. Okay, let us, since it is a last week for this course, so we will be solving, we will be making a revision of all the concepts briefly through which is being covered in this course. First, our course started with, our course is mainly divided into three main parts. First is a refreshment of thermodynamics. Thermodynamics, which basic concept such as first law of thermodynamics, second law of thermodynamics. So what is the Gibbs free energy of solution and Gibbs free energy of mixing, and how we will be calculating, and we will be understanding how the G versus X graph has been plotted. For example, if you have a one basic question may be asked in a different exam, R is, sorry, this is a isomorphous phase diagram. For example, this is a B percent. Then, so what will be the G versus X graph at different temperature? So if it is temperature axis. So this is a temperature T1, and this is the temperature T2, and this is the temperature T3. So at T1 temperature, this is a liquid phase and this is solid phase. It's a liquid plus solid phase. So at T1 temperature, So at different temperature, we can draw a G versus X graph. So at in the liquid phase, in the liquid at T1 temperature, the liquid phase is stable. That's why it is having the lowest Gibbs free energy. The solid phase will be like this. This is at T1 temperature. T2 temperature, I will be using a different ink. At T2 temperature, both liquid and solid phases are stable for particular compositions. So that's why we will be drawing. So this is the temperature. This is the composition where both. So liquid is stable here, solid is stable. So liquid and solid phases are both exist at this temperature. Whereas in T3 temperature, it will be similar case that of the T1 temperature, right? So here it will be where it is okay. So this is the thing at T3 temperature. So this is has been learnt in the refreshment of thermodynamics from lecture 1 to 10. So in the next series of lecture, we will be learning about the derivation of Fick's law, and continuity equation and basic concepts regarding with the diffusion has been learned in this second part of the video series, and we have also solved the solution for the mathematical solution for the diffusion equation. Such as here we have solved the obtained the mathematical equation for the homogenization of an alloy, and so diffusion in single component, diffusion in the multi component, Onsenger's equations. Different solutions are obtained in this video series. And next series is next part of this course is third part, mainly deals with the practical problems and practical situation where we are using this diffusion equations and application of these diffusion equations in the different practical aspects. For example, we will be solving the diffusion equations for the making the binary diffusion couples and multi-component diffusion couples, and using the Boltzmann-Matano method. Boltzmann-Matano method for finding the diffusion equation. Diffusion coefficient. Finding the diffusion coefficients. Okay. So today my handwriting is not that much good. I don't know why. Board is not working properly. Maybe. So, and we also used the body diagonal method for determining the interdiffusion coefficients, for designing as well as determining the interdiffusion coefficients for the more than three elements. If there is a system of more than three elements, that is quaternary alloys. Yes. Last part, that is, we have also learned the ternary phase diagrams. So how we are reading the compositions for all these all the different ternary alloys, and it can be applicable for any of the ternary alloy where we will be using the understanding the phases present in the each phase diagrams. And if we make the diffusion couples between terminal alloy of different positions of a ternary phase diagram, and we will be expecting or guessing the phases that is formed during the these alloys. So that is multi-component diffusion couples have also been analyzed with this type of phase diagrams. And in lecture 51, we have learnt about the analysis of a multi-phase diffusion couples, where the phase diagram looks like this. So this is a step has been occurred because of the a different phase that is formed between these two terminal alloy. This is a composition Ca plus. So between these two compositions, there is a one more phase has been formed due to which there is a step in the diffusion zone. And the last part of this video series, that is last 4 to 5 classes has been taught on the shortcuts of diffusion. So in this videos, like in previously what we have did is we have considered the single phase, where the all the like single phase, a single perfect phase, like we have not considered the dislocations, we have not considered the grain boundaries, anything we have considered. But in this shortcuts, how this diffusion plays a wide is affected by the presence of different aspects such as grain boundaries as well as the dislocation densities. So we'll be understanding the different, uh, like if there is a dislocation, how the diffusion coefficient will be affected. If there is any grain boundaries, how the diffusion coefficient will be changed for the particular elements. And we'll be solving the problems on these concepts in the upcoming hours of this session. And if you have any doubts, please ask. So, if you have any doubts regarding with any of the concepts that has been covered in this video series, so you can ask and free to ask, and you can also mail us, and you can also contact through a NPTEL a discussion session forum. You can post your problems and you can post your solutions, and we will be it will be useful for the fruitful discussions. So this is all about the diffusion course has been covered in this video series. So if you have any doubts, please let us know. And one more thing, I think you have registered for the exams that will be conducted through online computer based exams will be conducted, in which you have to bring your ID cards during the, and your center will be allotted, it will be known through your hall tickets. And one more thing is, like, you should not bring your physical calculator during the exams. There will be an online calculator, similarly kind of that gate exams, in which you will be given, and the demo of for the online calculator will be given in your the recent mail. Just clicking in that link, you will be getting the demo calculators. Yeah, just use through go through it and make user friendly, so it will be useful for saving the time. The practicing the calculator is also plays a vital role in the solving the problems, because since it is a problem based, and less of the theory questions will be also be there, and problem based questions will be also be there. That's why you have to practice the calculator. Next is, yeah, we will be moving towards the different problems that has been covered, important problems that is being covered in this video series. So first problem is related to the multi-phase division couples. So if you are given this phase diagram and asked to prepare a division couples, so if I given a terminalized composition vector, so predict the compositions that has been formed, or phases that has been formed during the division annealing. So after the division annealing, for example, I am just noting the points. Okay, so if you make a division couple between this and to this and to this point to this point, I will call this as A point and this is the B point. Please tell me the what type of a zone, diffusion zone, or a microstructure that have been that can be observed in this diffusion couple. First problem will test that. So we will be making the alpha aluminum. Yeah. Please tell me what type of a phase diagram it is. It is famous aluminum copper phase diagram. So where you will be understanding the aging effect of on the aluminum, how the hardness has been increased. Okay, so I will tell the further details about this phase diagram in the next few minutes after. First we will be observing how what type of a phase diagram that has been sorry what type of the phases are can form after the diffusion annealing. So if you are doing a diffusion annealing around six, so what is the diffusion annealing temperature I should give? Yeah, 500. That will be sufficient. Yes. So if I do the diffusion annealing, this is alpha aluminium and this is a theta. If I do the diffusion annealing for 500 degrees Celsius for 24 hours or some 6 hours, 7 hours. Okay. So in this case, one thing we have to remember, the temperature will plays a vital role in the formation of the different phases, whereas the time duration will increases the diffusion depth. It won't change any of the phases that has been formed. If you anneal it for 6 hours, 8 hours, 4 hours, it doesn't depend. The phases that should be formed is increased, just we will increase the diffusion depth. For example, I will tell you, if you do it for only for 6 hours, this may be the diffusion depth. If you do it for the 24 hours or 12 hours, the diffusion depth may be this much. Okay. Diagrams or phases that will be formed during this diffusion annealing. This is a simple question. This is alpha Al plus theta phase that will be formed during the diffusion annealing. Why it is so? Because see here. So the tie line that is drawn at a temperature of 500 degrees Celsius across these phases, it is first passing through the alpha aluminium. Yes. Then it is passing through the alpha plus beta aluminium. Right. Then it again reaches to the theta. So that's why it is forming the intermediate of alpha plus theta aluminium. So please let me know if it is heated to temperature of 550 degrees Celsius. So what type of diffusion zone is formed during this temperature? So if you draw at a temperature of 550 degrees Celsius, so what will be the phases that is being formed during this? Here, the first it is forming with alpha region, and again it is forming the three phase region. It's very interesting one. Alpha plus theta plus liquid, and here it is theta. This is alpha. So you can this one can also be extend to the other phases, such as here you can draw a phase diagram. You can draw by considering this point C and D. So you will be getting, so consider this as alpha 2 region. Oh, yeah, maybe alpha 2 region. Yes. So first gamma phase will be there. Yeah, tell me. So this is gamma and this is FCC CU, pure copper. So here in between these two, gamma, sorry, this is not alpha 2. This will be gamma plus Cu. So this is analyzed during this binary phase diagram. Similarly, in the ternary diagram also you can use it, and we'll be knowing in the upcoming series. Yeah, this is the second problem. So yeah, so we have seen the phases that is formed during the first binary phase diagram. Now we will be understanding in the ternary phase diagram. Let us read the question first. The following figure shows a ternary isotherm of a system ABC at a temperature of 1100 degrees Celsius. The dashed red line represents the tie line, and an isotherm diffusion couple assembled between pure B and alloy C and annealed for at a temperature of 1100 degrees Celsius for 2 days. The developed diffusion path represents the by the blue lines on the isotherms. Okay. Yes. So, which of the following schematic most accurately represents the possible diffusion structure developed in the couple between pure B and alloy C? Okay, this is a phase diagram, ternary phase isotherm diagram, where he is talking about this blue line. Okay, so this is the tie lines which represents the completions of alpha plus beta. And when we are moving from alloy 3 to pure B, so this is the diffusion path. So this is the diffusion path, DP, diffusion path, after the annealing of 1100 degrees Celsius for 2 days. So what type of phases that is formed during the, similarly, like what you have seen in the binary phase diagram, so it is extended to the ternary alloy. So initially, so my line is not that much accurate actually. So if you are plotting this, they are not getting accurate lines. This is B and this is Y3. So this is after diffusion annealing. This is a pure B and alloy 3. So first it is moving towards the beta C. So when we are moving from alloy pure alloy, diffusion path is showing the beta phase. Here it is, beta phase is there. Again it is moving towards the alpha plus beta. Okay, then again it is reaches to the alpha region. Finally it is reaches to the alloy 3. So this is the kind of, this is a kind of a microstructure that has been observed during across the diffusion zone. Yes. Let us understand the second problem. So in this problem 2 only, so second part is, so if you are doing the diffusion annealing between the alloy 3 as well as alloy 1, so what type of microstructure is been observed during the diffusion annealing? So one more interesting is here the it is passing through the three phase region. Okay. So if you are doing a diffusion annealing between alloy 3 and alloy 1, sorry, alloy 2 and alloy 1, so what type of, What type of uh, microstructure are observed? First, we have to follow the division path. When we are moving from alloy 2, first make it as alloy 2 first, and alloy 1. This is make it as alloy 2, and this is make it as alloy 1. Okay. So when we are moving from alloy 2 to alloy 1, first we'll be come across in the, first we will be understanding the, first we will be getting the alpha phase. Okay, this is alpha phase, and again it is moving towards the alpha plus beta phase. Okay, so this is alpha plus beta phase. After that, it is entering into the three phase region. See, alpha plus beta plus gamma. I think I have to plot it for bigger one. I have missed that one. What I have to do is I have to draw one more time. I will draw one more time. That will be the better, because so many phases are forming here, right? So this will be useful when we are having a ternary isotherm, as well as drawing the diagram will be the single phase. Yeah. So this is the phases that is formed during the alloy 2 to alloy 1. So first it is forming the alpha plus beta, alpha plus beta plus gamma, alpha plus gamma, gamma phase, and finally it is entering into the alloy 1. This is the kind of the microstructure that we will be forming when we are handling between the alloy 2 and alloy 1. Next question. So this problem we will take in the end of this session. So we will be plotting the ternary isotherm diagram online, and we will be identifying the different compositions. Yeah. So next problem is about a ternary infinite diffusion couple between the 80 titanium, 15 niobium, 5% of aluminum, and 50 titanium, 25 niobium, 25 aluminum was isothermally annealed at a temperature of 700 degrees Celsius for 48 hours. The location of the composition plane 70 titanium, 18 niobium, and 12% of aluminum was found to be at the at 200 microns at the end of 48 hours. So, what is the velocity with which the composition planes was moving at 48 hours of annealing? The location of the metanoplane was found to be at minus 300 microns. So read this question properly, and the hint is also given here. Please try to solve these question and find the velocity with which the velocity composition planes is moving. So in this one, he has given the x value. So which one will be the decreasing order? First, highest diffusivity in this value, surface is having highest diffusivity value, highest, and second is this one, the least diffusivity is in defect free lattice diffusivity. So surface is in this order only, I've given in the same order. Yeah, surface diffusivity will be the highest where the diffusion will be occurring. Okay, so this is the order of decreasing order of diffusivity. So if it is an increasing order diffusivity, this will be the reverse. Okay, next question is, so two body diagonal diffusion couples were assigned in a were designed in a ternary ABC system with a C bar as 30A, 30B, 40C, and C double dash will be the 10. So which one of the following couple should be the one of them? Yeah, please understand the problem first. Sorry. First, you need to take the, sorry, here we have to draw one more time. Okay, so he has given this point, that is C dash, and the difference between these is delta C is bar is 10. So if you first just, yeah, this will be the delta C by 2 first step, that will be the 5. First step is plus add all the composition to the C bar. Our C will be, new C will be delta C dash by 2 into C double dash, right? So first we need to add the all the to this given C bar, that will be the, for C1 that will be 35 of A, 35 of B, remaining is 35, 35, 70, this will be the 30, yeah, 30 of C. So which one will be the answer in this one? Okay, he has not given. One more time, so we have to do a subtraction here. Here it is 25 of A, 25 of B, then 50 of C. Is there any answer for this one? Okay, I think we have to give the, this is the correct answer. I think no answer will be given in this one. The E option is this one only. This is explained in the previous video series, the body diagonal method. So last problem that we will be solving on the shortcuts of diffusivity. In a single crystal aluminum sample, the dislocation density was found to be 10 to the power of 15 meter square. If the effective self diffusion coefficients and the lattice self diffusion coefficients in the single crystals were determined to be 4.14 into 10 to the power minus 15 and 1 into 10 to the power minus 15 respectively. What should be the pipe diffusion coefficients for aluminium at this temperature? Diameter of the dislocation will be the 1 nanometer. So he is asking about the uh, pipe diffusion coefficients dp. So the solution is given here. The given value are dislocation density, that is rho. He has given the rho value, and the effective diffusion coefficient is 4.14 into 10 to the power minus 15, and the diffusion coefficient is 10 to the power minus 15, and he is asking about the dp value. The dp value for this one is simple equation: d effective is equals to pi d square rho dp plus d. So this is given in our also explained how we have got this equation in the video series. Please go through that one video. So he has given the d effective, right? So he has given the d value, diameter of the pipe, that is dislocation, and okay. Uh, Substitute the values given in this problem, and the dp will be 3.14 into 10 to the power of minus 15 pi into 10 to the power of minus 18 into 10 to the power of minus 15. So this will leads to the 9.99 into 10 to the power of minus 13. meter square per second, dp value. Okay, so these are the problems that have been covered in this video. So if you have any doubts or queries regarding with this one, please let me know. So this is all about the course. And if you have any doubts regarding with any of the problems, please let me know through the discussion forum in the NPTL. Okay. Thank you. Thank you for the cooperation and thank you for the time.